This is Physics 2211, Lab 5 by Johnson, Josh, and Lim. In this lab, we're going to predict and analyze the motion of a slinky stretched out falling from rest and analyze the effects of its surroundings. So some questions to ask yourself during this experiment is, how does the slinky move? And does the bottom of the coated slinky stay stationary just like the one in the video? What we can conclude from this lab is that the bottom slinky will remain stationary for half of the time during the experiment, but the predicted model is slightly different than the observed model. Some important concepts to know in this experiment is Newton's second law. So that includes the velocity update formula, the F-net formula, and the momentum update formula. And something to note is that the system's change in momentum is proportional to the net force applied. Another force that we should know is the gravitational force, the drag force, which is the resistive force caused by the motion of a body through a fluid like air, and the slinky force, which is just the tension and is opposite of the gravitational force. For the observed motion, we're going to be studying this video by Veritasium, and we're going to assume that the object mass is about 0.2 kilograms and direct height is going to be around 1.75 meters, and the initial position will be depending on your calibration, and the initial velocity will be 0 because the spring is at rest. For the results, as you can see that the bottom of the slinky remains at 0, or it remains at stationary for a good amount of time before it starts falling down due to gravity. Now for the computational model, you'll be inputting the same initial conditions. So the ball mass will be 0.2, ball position will be obtained from the observed motion, and your gravitational value will be 9.8. You have to input your J hat, and the proportionality constant in this case will be 75. So the first part of the code will be when the bottom of the spring is at stationary. So you will have to include the total work done, which is the mass of the ball times by gravitational force times by J hat. And then from there you can get negative Ft, which is negative W, and then you get your net force. And from that you input the net force into your velocity update formula, and with that you can also get your position update formula. The second part of the while loop will be when the bottom of the slinky is falling down. You do the same thing. You include the work done on the ball in the F-net, and you input it back into the ball velocity, which will give you the graph in the next slide. As you can see, when you compare the observed and the predicted graph, you can see that the predicted one has a more straight linear line compared to the observed. So there could be a few reasons for this. Number one, the observed motion experiences fluctuations due to external forces that might not be accounted for. Or the other error could be inaccurate tracker point placement on the tracker software. So a few discussion questions to look at. Why does the bottom of the slinky remain stationary? It's because the forces in the y direction cancels out. Although the gravitational force acts downward, the slinky acts as a big spring and counteracts the force with a tension force of equal and opposite magnitude. Finally, if a heavier mass is added at the bottom of the slinky, will the spring still be stationary? It would depend. If the slinky has a length which gives a large enough spring constant, the weight will remain stationary until the top of the spring reaches the bottom of the spring.